Behind every perfectly timed flight, packed delivery van, or even establishing of a dream park, there lies a secret weapon: integer linear programming. This is the math that turns yes no decisions into real world wins. In this lecture, we are going to discuss integer programming problem, and specifically we will focus on one type of the integer programming problem. So let's start. The topics that we are going to discuss today are: we are going to first briefly discuss the types of the integer programming problems or models. Then we will see an example of the 0 1 integer programming problem, and then we will do its Excel solution. So there are three types of integer programming models. The first one is a 0 1 integer models, and this is probably the most, I think, the important type of integer programming model. And in this type of the problems, we are faced with making a decision, and then we uh, use the decision variables to decide upon something. So these are 0 1 integer models in which our decision variables, they either take 0 or 1 value. They are often called as the binary integer programming problems as well. Then we have total integer models in which all the decision variables are integers, not necessarily 0 or 1, but they can have any integer value. And then finally, with a general form of mixed integer models in which our decision variables can either be integers and some can also be non-integer values. So in this video, we are going to discuss a problem related to 0 1 integer models. So we are looking at a problem of a city council that is trying to decide upon decide upon building different activity zones, and four zones have been proposed: a water park, a skate park, a soccer field, and a climbing gym. The goal is to maximize the daily visitors while staying within the budget and space limits. So we are given with these four options. Each option has some expected visitors. This is the cost, and this is the space required for the water park, and similarly we have for the skate park, soccer field, and the climbing gym. And the goal is to maximize the expected daily visitors. So this is a maximization problem, and we have to maximize the daily visitors of for this park committee, for this park. So there are like two constraints for here. The first is for the total budget available, that is $130,000, and then 40 acres of land is available. And there is also a very important constraint, and that says that water park and the state park, they require the same flat paved area, so only one can be built. So you have to focus on the wording of this constraint that says only one can be built. So we'll come to it in a bit, but let's first look at the decision variables, because we are making a decision to do something or not. So the binary variables 0 and 1 are used. So we have x1, which will take a value of 1 if we build the water park, otherwise it's 0. So x1 is basically either 0 or 1, and similarly is the x2 and x3 and x4. So they are the binary decision variables having the value of only 0 and 1. Remember that this binary integer programming problems, binary integer programming or 0 1 integer, they are different from the total integer programming and the mixed integer programming. In total integer programming, your decision variables can have any integer values, not necessarily 0 1, they can be 100 200, any integer value. And in the mixed integer, similarly they can have the integer values as well as non-integer values. So here in this binary integer or the 0 1 integer programming problems, the values can either be 0 or 1. So now we can write based on this, we can, because we will have the objective of maximizing the maximizing the visitor. So this is the objective function, that is 280 into x1 plus 110 into x2 plus 3 into x3 plus 170 into x4. So this is our objective function. So we want to maximize z and the expected visitors per day. So the first constraint is $130,000 budget. So we have been given this cost. So we'll write 42,000 into x1 plus 8,000 into x2 plus 30,000 into x3 plus 75,000 into x4. This must be less than or equal to 130,000. And second constraint is about the space, 5x1 plus 5x1 plus 1.5x2 plus 8x3 plus 2.5x4. It should be less than equal to 14 acres of land. So these are, I think, very straightforward constraints. Now comes the turn of the key constraint, and that is only one can be built. So it's a very important constraint, and you have to focus on the wording which says only one can be built. So we have the water park, which is x1, and then the skate park, which is x2. So we are saying it like this type of constraint is called as the mutually exclusive constraints. So the type of constraints that are used in the integer programming, they are very important, and I'll explain them to you in a bit. But right now, understand that these two are the mutually exclusive, that either one or the other two can be built. So what's a truth table for it, I'll discuss with you in a while, in a minute. So the last constraint is the binary restriction, that is telling us that all of the decision variables, they should be either 0 or 1. So this is the complete model for us, and this is the objective function, these are the constraint, this is budget, this is the space, this is the mutually exclusive, and this is the binary requirement. Now let's dive deeper into this mutually exclusive constraint. So we have this wording that only one can be built. So this means that x1 plus x2 is less than equal to 1, because because we can only build one. We are not required to build one, but we can go for one. So mathematically this can be written as x1 plus x2 less than equal to 1. So if you look at the possible combinations for having this identity, having this equation to remain true, that if x1 is 1, then x2 must be equal to 0. Okay, then in this case this will be 1 plus 0 less than equal to 1. It will be true. If x1 is 0, then x2 is equal to 1. Again, this will be true. If this happens that you built water park but you don't build skate park, it will be true. You don't build water park, you build skate park, again it's going to be true. And because we have been told that we can build, so we can build only one can be built. So we can also drop the idea of building these two zones. So x1 can be 0 and x2 can be 0, and still this equation will hold. This last option, this is wrong. This can't happen, that we can build both. X1 is equal to 1 and x2 is equal to 1. 1 means that x1 is built, the water park is made, skate park is made, then 1 plus 1, it is not less than equal to 2. So this is wrong, this can't be done. So these are the three combinations for it. So this type of constraints are called as mutually exclusive, that if one thing happens, the other thing cannot happen. Now if we were told that exactly one must be built, before we were given can be built, now it must be built. That means that x1 plus x2 is equal to 1. Now this is called as the multiple choice constraint. So if you built x1, that is 1, then x2 must be 0, then this equation holds. If you don't build x1, then you build x2, again this is again okay, but you cannot build both. That is 1 plus 1 is equal to 1. It is not possible. So either x1 is 1 or 0, or x2 is 0 or 1. So this forces either water park or skate park can be built. Okay, another type of constraint that we come across in the integer programming is called as a k out of n constraints. So let's say we were told that out of the 4 options, out of the 4 zones, we can exactly 2 zones must be built. Out of the 4 options that we were given, the water park, the skate park, the climbing gym, and the I think let me and the soccer field, the 2 zones must be built. So we will write it as x1 plus x2 plus x3 plus x4 equal to 2. That means that any 2 of all these 4 can be made. So we are forcing ourselves by telling because we have been told that only 2 zones must be built. Another variant of this is at most k constraints. That means that instead of exactly 2 zones, let's suppose that we have been told that at most or no more than 2 zones can be built. No more than 2 zones. So we will write it x1 plus x2 plus x3 plus x4 less than equal to 2. Okay, so now again we have been told that we cannot build no more than 2 zones. So we can build 2 zones, or we can even drop the idea of building any zone at all. So let's say if we do not build all these 4, then again this will be 0. x1 is 0, x2 is 0, x3 is 0, x4 is 0. So 0 is less than equal to 2. Still it will be okay. So again, this is another variant of the at most k constraints. Then we have a conditional constraint, and that says that the skate park x2 can only be built if x1 is built. So x2 is depending upon the x1. So we will write it as x2 is less than equal to x1. So you remember x2 depends on x1. So while writing this, we will write the x1 here on the right hand side, remember, and x2 on the left hand side, because x2 is dependent on x1. So we'll write it x2 less than equal to x1. And if you look at the truth table of it, that means that x2 that if x1 is equal to 1, so then in this case x2 can be 1 or x2 can be 0. So there can be 2 options, that if x1 is 1, that x1 is built, then x2 can be built, or x2 might not get built. So this will be true. But if x1 is 0, then x2 must be 0, because if we say x2 is 1, and then x2 is 1 and x1 is 0, this equation becomes wrong. It becomes false. So if x1 is 0, x2 must be 0. If x1 is 1, x2 can be 0 or 1. So this is a very important constraint called as a conditional constraint. Then we have a correct constraint in which both must be built together. So x2 is equal to x1. So this means that if x1 is 1, if x1 is built, x2 must be built. If x1 is not built, that is 0, then the x2 must be 0. So summarizing all these constraints, we have mutually exclusive, at most 1, that meaning at most 1, then multiple choice constraint in which exactly 1, then k out of n, then exactly k or k exactly k, then at most k constraint, then will have maximum value of k. And then we have conditional constraint, that is j only if I, that is j depends upon I. Correct, in which xj is equal to xi. Now we are done with the mathematical formulation of this problem. Now we will move to the Excel and see how this is actually done. Okay, now I have a built Excel sheet here, and it's a pre-built sheet with the template, having the template for solving this problem. This was our original model with the constraints of budget, land, and the mutual exclusivity constraints, and this is the binary requirements. So first, we can see here is the zones that the water park, skates, soccer, and the gym. And then we have here this row in which this is an empty cells. So, and then we have here the constraints. This is the budget, this is the space, this is the mutually exclusivity constraint. Okay, so, and then we have here something called as the usage. What is this? Basically, this is the formula. In this usage, we will write the formula for writing the constraint equation. Okay, and these are our constraint equations. So we will plug in the formula in these cells, and this is the available. This is basically the right hand side of constraints. This leftover is basically, this is the what was available, that is available minus the usage. This is the leftover. And these four cells, these are very important cells here. Now these are the cells in which we are going, these are purposely kept empty, and these cells represent x1, x2, x3, and x4. So the values of x1, x2, x1, x2, x3, and x4 will be chosen by the solver in these four cells. And then this is the total daily usage. This is basically used to write the formula for objective function. So how it is done, I'll show you. Okay, so let's first remove these things, and just to make the space clear. Okay, so okay, let's discuss. Let's start with the with the coefficients. This daily usage, this is the coefficients, and this coefficient is 280 of the for the x1, and then 110 for the x2, then 380 for the x3, and 170 for the x4. Now these four cells, they represent x1, x2, and x3. So I'll just delete the formula here. And so the objective function is, what is the objective function? This says that 280x1. So 280x1 means 280 multiplied by this cell plus 110 multiplied by this cell plus 380 multiplied by this, and 170, and so on and so forth. So I'll write the formula here, and this formula is 280 multiplied by x1 is this one, plus 110 multiplied by this skate park plus soccer multiplied by x1, plus the daily usage for gym multiplied by climb by the x4. So this is our formula. So what we have done, we have written the formula here. Now let's write the constraint here. The first constraint about the budget, it says 42,000 for the water park, 8,000 for the skate, and then 30,000, and then 75,000. Okay, and this is right hand side of these constraint. The right hand side here is 130,000. Okay, now the other constraint is for the land is 5, 1.5, 8, and 2.5. The right hand side is, let me just delete it now so that it is visible to you. Okay, And this is for the contingency, that is the mutually exclusive. It says x1 and x2, so we have with x1, it is, we can write it as 1x1 plus 1x2. So we will have right here 1 and 1, and there is no x3 x4, so we'll keep the cells empty, and here it is 1. Now these signs of less than equal to, they are just for the cosmetics. They don't really mean anything for the solver, but I have written here just to show the inequality relationship between the constraints. So the leftover is basically, it is equal to the, available, which is given as here, minus the usage. Okay, so let me now delete it. Okay, so I'll just drag it, and this way you can see. Now comes the usage, and as I mentioned, I told you that usage is the formula for writing the constraint. So if the first constraint is equal to 42,000 multiplied by x1, and x1 is here. Remember, x1 is this one. This is not x1, this x1, this is, these are the just description of x1, x2, x3 and x4. X1 is here, multiplied by this, plus 8,000 multiplied by x2, plus 30,000 multiplied by x3, plus multiplied by this one, climbing gem. So this is our constraint. So I'll just, let me just copy it. I can just copy it, and then I'll paste here, and because now we have to move to the space, and I'll just put it here, move it downwards, so the formula is okay. Now the formula is for the land, and again I'll just copy it, and I'll copy this one and this one here. We don't need the last two parts, so I will just delete it. Okay, so this is all done. So now let's move to the solver. We have set the problem. Now let's start the solver. When you click it, we have the option of maximizing, minimizing. So we want to maximize, and this is our objective function, and we have to we will maximize it by changing these four cells, x1, x2 and x3 and x4. And now we have to add constraints. So these three are constraints, because in these three cells we have written the values of the equations for the constraints. So I'll select I'll select these three, and because I mentioned to you earlier that these values, these signs, they have no significance for the Excel, because they are just for the cosmetic purpose. It's already mentioned here. We can choose from here less than equal to, and then what are the constraints. The right hand sides, we have chosen this one, so we add this constraint. Now if you see that we have already added these three constraints, now let's add the binary constraint as well, and this tells us that all these values x1, x2, x3 and x4, they must be binary. So there's the option of binary, so we select binary from here. So it's okay now. So the option, the algorithm is simplex options. Just check, sometimes this is checked, so make sure that this is unchecked. Now the algorithm is simplex LP, so everything all set. So let's solve it. Okay, hooray, yes, you see, we have solved the problem. We have found the feasible solution. So let me just delete these annotations so it is clear to you what we have found. So we have found that we can maximize the visitors to 660 per day, and we can do it by just spending 72,000. So this is the real cost optimization. We have saved 58,000, and by just choosing the water park and the soccer field, we have maximized the visits per day, and they are 660, and in this process we have used $72,000 out of the $130,000 available to us. And we have also uh, we have also saved $58,000 and 1 acre of land. So you see, this is the power of the optimization. By using the right optimization technique, you can make brilliant decisions, you can make the right decisions. So the zero one integer programming, it provides you with the basic maths, the very interesting and important maths to make the right decisions. So hopefully you enjoyed this tutorial. Stay tuned to this channel and please subscribe if you have not already done. Thanks for watching.